Okay, let's continue our structural irregularities. This is the second part of the structural irregularities, and now we will focus on the horizontal irregularities. Just like the vertical irregularities, we have also 5 types of different horizontal irregularities, starting from torsional irregularity to non-parallel systems irregularity. Okay, let's start with the torsional irregularity. So, what is a torsional irregularity? As you can see, if we have an horizontal irregularity, is that uh, during earthquake, our structure will also move, will also rotate. No? It does not just move in the orthogonal directions, in the north, south, or the east-west direction, but it can also rotate. No? So this rotation will determine if there is a torsional irregularity, and according to the NSCP, torsional irregularity is defined as something, no? So torsional irregularity shall be considered to exist when the maximum story drift computed along the accidental torsion. So accidental torsion, this is in NSCP, this is we consider the accidental torsion as equal to 0.05, no? So uh, at one end of the structure is more than 1.2 times the average of the story drifts. So as you can see here, if the maximum drift in this plan, in this horizontal plan, is greater than 1.2 times the average. So how can we get this average? So average is just the minimum drift, maximum story drift, or the rotation here, maximum story drift, plus it's the average, no? It's the average of maximum and the minimum. That's why we call it the maximum story drift. Average story drift, I mean. So in ASCE 7-22, we have 2 types, no? So in NSCP, we only have one type, type 1. So in ASCE 7-22, we have 2 types, regular and extreme. So we can call it a regular torsional irregularity if it is less than 1.4 but greater than 1.2. And we can call it extreme if the drift max is greater than 1.4 times the drift average of the horizontal plan. We can have an example here with this one. So we go here, torsional irregularity. As you can see, suppose building A has a drift, no? Has a drift minimum of this one and drift maximum of this one. So in each floor, we have both maximum and minimum drifts. So how can we get the average? We just get the average. So average is this one, and enter. So average is just the average, no? We sum them and divided by 2. So let's just ignore this one. Okay, so we got now the average of the minimum and maximum. So what is the minimum? So the minimum is the minimum drift, and the maximum is the maximum drift, and average is the average of the 2. So let's see. So if we have a ratio here of greater than 1.2, then but less than 1.4, we call it a regular torsional irregularity. But if the ratio is greater than 1.4, it is extreme. And if the ratio is less than 1.2, then there is no torsional irregularity. So always remember that during an earthquake, our building will also rotate. And it depends on the maximum drift and the average drift and the minimum drift of the structure during earthquake. So let's see. So the equation here is just maximum divided by average. So let's see. I will drag here. So as you can see here, we don't have a we don't have a torsional irregularity. So building A has no torsional irregularity. Suppose that our minimum, no, our minimum, or in this ground floor, no. Suppose that in ground floor, our minimum drift, suppose this is just 0.75. Then let's try. So as you can see here, we now have an extreme irregularity. So by making the minimum drift in ground floor having gikalahati natin ang minimum drift. Then therefore in the ground floor we have an extreme. But anyway, in our original data, we don't have an torsional irregularity. All of them is just 1.11, 1.09, 1.10. So therefore there is no torsional irregularity. Okay, now let's go back here. So next, our irregularity for horizontal irregularity. So we call it horizontal because it's all about the plans. It is about the horizontal plans. So the floor plans, the what we call that, the floor framing plans, that is why it's called horizontal irregularities. Earlier, we call it vertical irregularities. It's because it's between the different floors. So vertical, no? Vertical. It's for the elevation plan. So, what is the re-entrant corner irregularity? Suppose our structure is not just a simple rectangular plan or has a rectangular footing, but as you can see here, we have a letter L shape of a building. We can have re-entrant corner irregularity if the re-entrant corner, the PY and the PX, this is what we call the re-entrant corner, is greater than the 15% of the plan dimension Ly or Lx. So, if it's greater than 15%, let's say we can have, what is the 15% of this one? Suppose this one is 20. Okay, it's so big, no? Suppose this is 4 meters, and this one is just 6 meters. Okay, it's obvious that 4/6 is almost about greater than 50% because the 50% of 6 meters is 3 meters, so it's greater than. So it's almost, so we can therefore say that 6/4 is greater than 15%, no? 15%. So by doing this, we now have what we call the re-entrant corner irregularity because 6/4 is greater than 15%. Same with this one. If this is also, let's say this is 3 meters, and this is 6 meters. So 3/6 is 50%. So it's already greater than the 15%, the 15% threshold. Now therefore, we have what we call the re-entrant corner irregularity. So this is just straightforward. So as you can see here, irregularity exists if the re-entrant corner is greater than 0.15 of the plan dimension in each direction. So, okay. Next, we go to what we call diaphragm discontinuity irregularity. So, from the word diaphragm, in the context of horizontal plans, diaphragms can mean slabs. Yes, we can consider slab as the diaphragm of the structure. We can have discontinuity if okay, let's see the definition. If there is discontinuities, no, including those having cut out or open areas greater than 50% of the gross enclosed area, or changes in effective diaphragm stiffness of more than 50% from one story to the next. So let's consider this first part. So if the area, let's say, if this area is, let's say, 30 square meters, and this enclosed area, this total area is 60 square meters, greater than, no? So let's say 62 square meters. So as you can see, 62/30 is greater than 50%. So therefore, in this scenario, we have a diaphragm discontinuity irregularity. So for this, what we call the effective diaphragm stiffness, no, it's about, let's say, example, shear wall is also diaphragm. So if the stiffness is more than 50% from one story to the next, then changes. We can also have diaphragm discontinuity, but in this scenario we only consider the cutouts, no, the opening. So why is it that we have an opening per floor? It's obvious that it's also what we call the stairs. Okay, so stairs, it's obvious that we really need to cut, no, to have a cutout in the slab so that the stairs can can, because of the stairs. Okay. So next, this is also straightforward, nothing to do. Just remember the 50%. Then we have the out of plane offsets. So this irregularity is about this out of plane offsets in such a way that, let's say we have this shear wall here, and the shear wall is another here. So we have this what we call offset. So earlier we have what we call the geometrical offsets in the vertical part, but this one is out of plane offsets. So we can find, no. So there is no such thing as threshold, but if we can have a discontinuity in lateral force plot, let's say this is a column in the second floor and another column here. So automatic, we now have what we call out of plane offsets. So it's almost the same with the vertical part of the offset, in the vertical part where we can see that the horizontal dimensions is less than the offset. So you remember the vertical one, offsets. Diba? So in the vertical we have that what we call it the vertical, no, vertical offsets, irregularity, and this one is what we call out of plane offset. So we can have another example, this one. So we have the vertical offset. So the difference between the vertical and the horizontal out of plane offset is the force, no, is the path, is the load path of the force. Okay, so we can see here the wall above is here and we have a wall below here, that is also an out of plane offset. So from the word out of plane, then we can also have this one. So it's just about an offset. So if there is this type of structure like this, then automatic we have an out of plane offsets regardless of any percentage, because this is there is no threshold here. So next is the non-parallel systems irregularity. As you can see, it's really obvious. What does the non-parallel is that the shear wall or the columns are not parallel, but this is mostly seen in shear walls, no? So you can see we have a shear wall here and we have also a shear wall here, and they are not parallel, so we can call this one a non-parallel systems irregularity. So the vertical lateral load resisting systems are not parallel to or symmetric about the major orthogonal axis. So as you can see here, the plan, our two orthogonal dimensions is this one, and in this one. So that is the main orthogonal. So as you can see, we have this shear wall that is not parallel with the orthogonal axis. And if we can find something or load resisting elements, vertical load resisting elements, in this case, let's say shear wall is not parallel to the orthogonal axis, then we can say that there is a non-parallel systems irregularity. So this also an example. If our building is a non-trapezoidal, this is really has no what we call parallel systems. And this one, so we mostly find some designs of structures like this, and therefore this is automatically what we call a non-parallel systems irregularity. No threshold, just if there is a load resisting system, beams or shear walls, it's automatic that is not parallel with the major orthogonal axis, in this case direction x and direction y, then therefore it is a non-parallel systems irregularity. So now we have finished the 5 types of horizontal irregularities, and in the previous video we have also finished the different vertical irregularities. So we have 5 types for horizontal and we have 5 types for vertical. So now what if structural irregularity exists? So mostly structural irregularity exists because of the architectural plans, and there's no problem with that. The only problem is the extreme weak story. So if there is an extreme weak story, we must do something because there is a system limitations. And again, the system limitations is set forth in NSCP. It says that if there is an extreme weak story, it is not permitted if the stories are above 2 stories or the total height is above 9 meters. So it's already forbidden if we have an extreme weak story. So there's an exception, but we just stop doing weak story, extreme weak story. So structural irregularity is permitted as a whole, no? So what shall we do if there is a structural irregularity? First, the first thing that we should do is that we shall always use dynamic procedure. So, for design, we really need to have the demand. No? We cannot design our structure if we have the demand. So, NSCP 2015 provides two types of determination of design earthquake loads or the demand. The first one is the static force procedure. So, static force procedure is just simple, but if the irregularity exists, it's automatic that we always use the dynamic force procedure. So, the dynamic procedure is either a response spectrum analysis, which is, we have that in another video, or time history analysis. For simplicity, response spectrum analysis is enough. It is considered as dynamic procedure according to NSCP. So, I will not discuss here more about response spectrum analysis, but you can do it in your own. No? I'm just discussing here about the different irregularities. So next is another is that it's automatic. No, it's good that we use a three-dimensional model. So we can design our structure in two-dimensional, but especially if we have a horizontal irregularities, we should consider three-dimensional model partnered with the dynamic procedure. So there is also an exception clause, no, but we should just use three-dimensional model. Then finally, we should consider this load combination also. So that is just the correct way of dealing with irregularity. Irregularities in a structure is not forbidden except the extreme weak stories. And any plans or designs by the architect can be designed well, can be safe and have a good structural design. Just remember that these three, if irregularity exists, number one is we use dynamic procedure, and number two we use three-dimensional model. So thank you. Please also watch my video about the response spectrum analysis on how we can properly put response spectrum analysis for our design. Thank you again.